So good morning or good afternoon. Thank you very much for coming. I commend your bravery, because not only is this a talk in an English language, but it's also been marked as a hardcore talk, so I guess you all guys are hardcore. And even though there are two other perfectly fine sessions happening in parallel, you're all here. So thank you very much for your interest in .NET cryptography. I assume you guys know as much as I do that this is an important topic, and that's why you're here. So let's begin quickly about myself. My name is Stan Drapkin. You can see my email there. I'm a Chief Technology Officer of an IT company which predominantly focuses on cybersecurity and regulatory compliance. I'm also an open source author of several libraries that were rather well received. One of them is called Inferno. How many of you guys have heard about Inferno? Okay, I can see some hands coming up, that's good. So that library focuses on getting the .NET high-level encryption or cryptography story right. And the second library that I've authored is called TinyORM. It focuses on improving the .NET story of micro-ORMs. I've also written a couple of books that might be relevant to this talk. The first one is called Security-Driven.NET from 2014, and the newer book is called Application Security in .NET Succinctly. So let's proceed, and today I will talk about the following things. I will set the stage by giving you my version of what I call the 4 stages of crypto enlightenment, just to get us all thinking about cryptography in general. And then I'll delve into the 2 main sections of my talk. The first section will be on symmetric cryptography, and the second section will be on the asymmetric and hybrid cryptography. So in the symmetric crypto part, I will briefly compare low-level versus high-level cryptography, and I will show you an example of streaming cryptography, or streaming APIs. And in the second section of my talk, we'll have lots of fun with RSA, I promise you. And then I will introduce modern elliptic curve cryptography and its primitives. So let us proceed. I'll first introduce you to what I call the 4 stages of crypto enlightenment. The first stage is what I call XOR is awesome, look mom what I can do. Hopefully, I see some smiles there. Hopefully you all have been there, or most of you have been there. You've seen the wonders of the XOR function, and you've marveled at what can be achieved with it. But most of you have hopefully grown up from that stage, and you've moved to the next stage. And the next stage is typically what I call someone's ability to encrypt and decrypt with AES. We've all learned that there is this well-known, well-received algorithm called AES, Advanced Encryption Standard, and we learn how to use it and its APIs. And that's the state where most of the developers that do not attend .next typically reside, and they don't advance from there. But you guys are not in that group. Clearly, you attend .next. You have probably been to some of the past .NET talks, and you've moved from there. So the next stage is once you reach another level, you attend various talks that talk about the dangers of low-level APIs, you realize that in many cases what you've been doing so far is wrong, it's inadequate, and what you should really be doing is using high-level APIs. And just for completeness sake, I will mention the last stage, or the 4th stage in my nomenclature, which is a stage where a better solution might not need cryptography at all. So this is a more elusive, rare stage. There is a quote that I like that supports this later stage. It's a quote by Dr. Peter Newman, and it says that if you think cryptography is the answer to a problem, then you do not know what your problem is. So if the time permits, I will actually show you an example of that rare stage. So with that stage being set, let us proceed, and we'll get right into the meat of my presentation, the first section on symmetric cryptography. So we've been told many times and in many other .next sessions and other sessions that low-level cryptography is dangerous. Its APIs are dangerous. There was a great talk from a past .next conference from 2015 by Vladimir Kochetkov. He's actually here. It was titled Pitfall of System Security Cryptography, and it's available freely on YouTube. If you haven't seen it, I do encourage you to check it out. In that talk, one of the main points that Vladimir made was that every step of low-level cryptography is filled with decisions. All kinds of decisions that you are not aware that you need to make, and more importantly, in many cases, you're not even qualified to make. And one of the key takeaways of that talk was that low-level cryptography should ideally be avoided. And what you should be using instead is high-level cryptography. So that's all great. It sounds like a great plan. It's a great advice. But what this asks for, the question that it begs, is whether you guys, whether you yourselves are able to know what a high-level cryptography is, or rather what it should be. So let's think about that a little bit. And in order to do that, we need to first identify the symptoms of a non-high-level cryptography. What do we typically deal with, which is a non-high-level API? So let's try to enumerate some of them. So the first thing that comes to my mind is that the API that you are probably using today doesn't feel .NET native. In other words, whatever you're using or working with feels more of a low-level wrapper than a high-level API. The API is easy to misuse, in other words, to use incorrectly. The API forces you to generate all kinds of strange, weird things, like nonsense or initialization vectors, things like that. The API can force you to make all kinds of uncomfortable decisions that you might not be prepared to make, such as choosing algorithms, padding modes, key sizes, nonces, IVs, tag sizes, etc., etc. There's a long list. The API that you might be working with doesn't have a good streaming API, and I'll show you an example of what a streaming API is. So with that being said, what is a high-level API? Or rather, what is our wish list? What do we want the high-level crypto API to be? So let's quickly summarize that. So in my opinion, high-level crypto API, first of all, should be intuitive. It should be intuitive and eloquent to both read and write. I think that's very important. It should be easy to learn, so the learning curve should be very low. It should be easy to use, and at the same time, it should be very hard to misuse or to use incorrectly. It should also be very powerful. So what that means is that it allows you to achieve your objective with very little effort, without a whole lot of code or other things that need to be done. And last but not least, the API should be low friction. So what I mean by that? The API should just work. It shouldn't have a long list of caveats or constraints or special cases or things that you need to worry about and keep in mind. It should just work, no questions asked. So once we know what we want from a high-level crypto API, how do we find a high-level crypto API or high-level crypto library for .NET? Well, we could Google, but that would be too easy, right? You guys are professional software engineers. You come to .next. Googling is not our way, wouldn't you agree? We're going to go the hard way. And the way we're going to do that is, instead of Googling, we're going to research, and we're going to try alternatives. So before we do that, there are some basic concepts that we need to cover so that we have a good mental model of authenticated encryption that will help us on our journey. So let's start by saying that we will have our plain text P of variable length that we will want to encrypt. And we will transform that plain text P into the ciphertext C of the same identical variable length, just for simplicity's sake. And that transformation will happen under some secret key K. So far I'm keeping it rather simple. In addition to the ciphertext, we'll also have a fixed length authentication tag T that we will also produce. And there will also be a fixed length nonce N. So in addition to that mental picture that you see in front of you, I also want to introduce two additional concepts. So the first concept is this thing called N bar, or N with a dash on top of it. So N is the nonce that you see there in yellow, and N bar simply means a reuse of that nonce. So whenever you encrypt and you happen to reuse the exact same nonce, that will produce a nonce collision. That's what N bar is all about. And as some of you might already know, nonce reuses, when you encrypt under the same key K, lead to compromises of confidentiality of plain text, which is a bad thing. So N bars are to be avoided. It's an undesirable thing to have. And the second concept is something called AD, where AD stands for associated data. It is optional data which is authenticated, but it's not participating in encryption and decryption by itself. So that's going to be our model for the next set of slides. So now that we are equipped with that model, let's look at our alternatives, and let's try to analyze an open source library that provides encryption in .NET called libsodium.net. How many of you have heard of libsodium.net or have used libsodium.net? Okay, good. So I see some hands coming up, so there is some familiarity. Great. So let's take a look at what it offers us. So here's some C# code that you can use to do authenticated encryption in libsodium.net. At the first glance, it seems reasonably eloquent, reasonably simple. On the first line, you generate a nonce, and then you plug that nonce into the second line where you do the encryption. So you encrypt some plain text P under that nonce, some key, and optional associated data. And on the third line, you do the exact same thing, only you convert ciphertext back into plain text. So far, so good. What can possibly be wrong with that approach? So the first thing that you need to know about Libsodium is that there are actually 3 different ways of doing it in Libsodium API. They provide you 3 different methods of doing it. You can see them on your screen. And that obviously begs the question, okay, so now that I'm faced with 3 different approaches, which one am I supposed to use? Which one is better? Which one is worse? Which one is undesirable, et cetera, et cetera. So in order to answer that question, we need to go deeper. We need to look at under the hood. So let's do exactly that. So the first method there happens to use AES GCM crypto primitive with the 96-bit nonce, but more importantly, it has a rather long list of constraints. For example, you cannot or should not be encrypting more than 550 gigabytes per key with that approach, or 64 gigabytes per message, or encrypt more than 2 to the power of 32 messages in general. And it's not like the library is going to warn you that you're approaching that limit. It's something that's now your burden. You're supposed to police that and not to exceed that limit, which is another burden on yourself as a developer trying to consume this. So moving on, the second approach there uses another cipher suite called Chacha Poly with a much smaller 64-bit nonce. And that nonce is way too small for comfort. It's very easy or very likely to generate collisions with such a small nonce space, and for that reason alone, that approach should not be used at all as a general purpose approach unless you really know what you're doing, unless you're an expert in the field. And the third approach, before I show you the details, one of the things that you'll notice about the third approach is that in the APIs and the parameters, there is no associated data. So if you want to do authenticated encryption with associated data, the third approach is off the table right away because it just doesn't support associated data at all. The particular cipher suite that it uses is yet another algorithm called X Salsa Poly. The nonce is much larger, it's a 192-bit nonce, but the missing associated data is a big constraint there. So now that we looked at it at a glance, let's try to think about some other questions that arise when we try to use libsodium.net. So that nonce that I've shown you that gets generated in the very first line of each one of those 3 approaches, what are we supposed to do with it? What does the library say that we are supposed to do with it? The library is completely silent on that. In other words, it's your burden to figure out what to do with it. Chances are that you will be manually appending or prepending it to the ciphertext somehow, but now it's your burden. The associated data in the first 2 methods should be allowed to have any length, right? Well, it turns out that the answer is no, and the library supports 16 bytes max, because 16 bytes should be enough for everybody, right? What happens on decryption failures? So that particular library made the decision to throw exceptions. You're going to have all kinds of exceptions if corrupted cipher streams are a thing in your environment, and you would need to deal with those exceptions. What do you do if your secret key is not exactly 32 bytes? Again, the library is completely silent on that. In other words, it's your problem. You're supposed to figure out what you do with it. The library must have its keys equal to 32 bytes in length. And the reuse of byte arrays is another important topic. If you want to reuse some of the byte arrays that get generated, so for example, in the very first line there, you saw a byte array being returned for the nonce generation. If you want to reuse those byte arrays for high throughput scenarios, where garbage collection pressure is something that you care about, with that particular library, you cannot do that. It will always generate a brand new byte array every time when you generate a nonce. So let's quickly compare it visually using the framework that we already have, we are already familiar with. So that first algorithm that Lipsodium provides uses AES GCM. The 96-bit nonce is there in yellow. It's less than 128 bits, but it's still not too small. So it's somewhat uncomfortable, but not too uncomfortable, I would say. The second column there, the bluish one, you see two numbers there. The first number is in bold. The 128 refers to the amount of storage that the authentication tag T occupies. So that tag is precisely 16 bytes when stored. And the second number that you see there in brackets, where it says less than 128, refers to the amount of entropy, or let's say randomness, that is actually captured in that stored tag. So even though the tag itself is 128 bits, the amount of entropy is actually less than 128. How much less? In this particular algorithm, that actually depends on how much data you encrypt with it. So the more data you encrypt with this AES GCM approach, the weaker your tag becomes. And in any case, it will be less than 128 bits of entropy for the tag. So that itself is concerning. But even more concerning is the white column there, which says that nonce repetitions or nonce collisions will lead to forgery of all ciphertexts that were produced under the same key K. So even if you have, let's say, 100 blocks or 100 ciphertexts, and only two of them happen to collide, so only two of them have the same colliding nonce, that colliding nonce will internally leak the authentication key, and that leaked authentication key will allow an attacker to forge every other ciphertext that has ever been produced under the same key K. So this is a pretty big concern and a pretty big constraint on that particular approach. So moving on, the second method that Lipsodium.NET allows you to code against, as I mentioned, uses a very small nonce space, 64-bit nonce space, which is way too small for comfort. The tag story is somewhat simple. The tag also uses 128 bits of storage when stored, but the amount of entropy is actually only 106 bits or less. So this is way less than 128-bit security level that most people try to target. The forgery story is slightly better. Not by a whole lot, but slightly better. When you have nonce collisions, and as I said, nonce collisions are way more likely under this method, they will lead to forgery of all ciphertexts, but only for the blocks where the nonce happens to collide. So in my early example, where you had only 2 blocks out of 100 where the nonce was colliding, only those 2 blocks of ciphertext can potentially be forged, rather than every single ciphertext that was produced under the same key. And the last method has a very large nonce, 192-bit nonce space, which means that nonce collisions are not probable, highly not probable. The tag story is the same because the same authentication method is being used, 128-bit tag with less than 106 bits of entropy. So compare all that to, for example, an approach used by Inferno library, where the nonce space is huge, humongous, which also means that nonce collisions are impossible or highly not probable. And the tag story is crystal clear and simple. There are exactly 128 bits of storage used by the tag and exactly 128 bits of entropy. So this is a conservative, safe, correct approach. Before we get maybe deeper into Lipsodium.NET, we need to understand its purpose, because what I think many people, and especially those of you who are already using Lipsodium.NET or are familiar with it, do not understand is the very purpose of Lipsodium.NET. And in order to uncover it, we need to look at its documentation. So if you read its documentation, it will say that Lipsodium.NET is a C# wrapper around Lipsodium. Okay, that sounds great. So we need to look at Lipsodium, which is another open source project. So let's take a look at its documentation. And Lipsodium docs say that Lipsodium is a fork of NACL with compatible APIs. That sounds great. So let's take a look at NACL, which is yet another open source project. And its documentation says that NACL's goal is to provide all of the core operations needed to build higher level cryptographic tools. So this is your aha moment right there. The very purpose of NACL and all the other wrappers on top of that is to provide you the core low-level primitives that somebody else would then use to construct and build higher-level cryptographic APIs. It was never designed as a high-level cryptographic library. So just bear that in mind. And the point I'm trying to make is that if you actually need and want a high-level crypto API, simply find, identify, and pick a good high-level crypto API library. Don't try to take some low-level library wrapper and pretend like you're doing high-level cryptography, because you're not. So let's take a look at how we could do authenticated encryption with something like Inferno. Again, encryption and decryption are both one-liners. You simply encrypt some plain text with a key and optional associated data, and then you decrypt the ciphertext with a key and the optional associated data. Very simple story. The things to note are that there are no nonsense that you have to worry about. There are no decisions that you need to make. Decryption error produce null plain text, which means that nothing is thrown and you can safely use it in a high throughput environment where you're not putting additional pressure on garbage collection because creating exceptions is expensive. And this kind of approach is a win in my book, and hopefully I've been able to convince you of that. So let's have some fun. Let's try to encrypt some strings. Encrypting strings should be easy, right? That's the hello world scenario of cryptography. Everybody should be comfortable using that or implementing something like that. So let's assume that we have only two possible string values, the string left and the string right, and we're going to encrypt them. So here you see some code. I'm using Inferno here, but it doesn't really matter which library you're using. So we're just encrypting left and right with the same key. And then we are obtaining two ciphertexts, C1 and C2. So this kind of approach is production-ready code, right? Or does anyone see a problem with this approach? Would you guys deploy to production? Go ahead. What's the issue with K? So let's say that so I don't think the key here is the problem. Let's say they're both using the same key and the key is of adequate length. So what I'm alluding to here is that if you just look at the ciphertext, if you just look at C1 and C2, you would probably be safe to assume that C2 will be longer than C1, at least with the normal cryptographic approaches. And that length of C2 is something that's called length leaking. So C2 in many cases will be 1 byte longer than C1. And that length leaking itself will be it will allow an adversary to identify which plain text, which particular string was encrypted, whether it was left or right. So an easy way to fix it in this particular scenario is, for example, you can try to make sure that both of your strings are of the same length. So you could think about maybe appending an extra character to the word left, so that both left with another character and right are exactly 5 characters long. So that will prevent that problem from happening here. So this length leaking that I've just shown you, that's not a real problem, right? We don't really see it in real applications that are deployed out there, right? Well, in January 2018, relatively recently, there was an article in Wired magazine about a research done by a company from Israel called Checkmarks, where the article was titled Tinder's lack of encryption lets strangers spy on your swipes. And just so that everybody's on the same page, I'll probably butcher Tinder, but I'll give a crude description of what it is. It's an app that receives, I guess, a photo stream, and then users swipe left or right on different photos to show whether they like or dislike a photo. So the problem that the researcher uncovered was that even though the actual swiping commands, the swiping left and the swiping right, was all properly encrypted. They used TLS and HTTPS and it was all properly encrypted, but researchers figured out that the whole suite of commands for swiping left occupied a different amount of bytes than the suite of commands for swiping right. And that allowed them to determine whether the user was swiping left or right. That by itself is a vulnerability, but it's not that big of a deal. But the problem for Tinder was the fact that it was aggravated by the fact that the actual photo stream that they sent to your devices was sent over plain HTTP, completely unencrypted. So any adversary was able to figure out not only whether you were swiping left or right, but what was the exact photo that you were looking at when that swiping occurred. So that created a much bigger vulnerability, obviously. So it is real. So my point here that it is real, length leaking is real, and something that we all need to watch for. So let's have some more fun. Let's try to encrypt a file. How hard can that be? So with something like libsodium.net, the first thing that you realize is that file encryption, or in a more general term, streaming encryption, is not available out of the box. If you want to encrypt a file, it's something that you have to build or do by hand. And trust me, it's not something that you want to do manually because you will not get it right. With something like Inferno, the situation is much better. Here on your screens, you see an example that's almost taken verbatim out of MSDN. It's a very simple case of two file streams, one for the source file and one for the destination file, and a crypto stream that converts from the source stream to the destination stream via a transform. So Inferno itself is used on one line only in this code sample, the line with the comment. So it's a very simple use case of using Inferno. It's a one-liner solution to getting a full-blown, fully working and validated authenticated encryption over streams going. Another thing to be aware of is that there are message limits when you're trying to encrypt with the same key. So in Inferno, the message limits are there, and they're on the screen, but these limits are so large that in practice, you don't have to worry about them. You can assume that there is no limit because you will never practically get to it. With something like libsodium.net, the limits are there, and they're different because, as I've shown you before, there are at least 3 different algorithms or 3 different approaches that you could use with Inferno. Each one has its own limits. But the important thing here is that these limits are low enough that it is practical for you to hit them or reach them. So it is something that you need to worry about, and you need to check whether or not your particular use case would ever run into those limits. Another thing I'd like to introduce to you is this notion of associated data, which I don't see covered in many other places. There is this notion of weak associated data, where the associated data itself is only being authenticated, but other than that, it's not participating in the actual encryption and decryption process. Compare that to the notion of strong authenticated data. So under the strong notion, the authenticated data is not only being authenticated, but it is also actively participating in encryption and decryption process because it actually alters the very process itself. Inferno happens to use the strong notion of authenticated data because encryption itself relies on the authenticated data as the internal encryption tweak, while most other libraries that I've seen, that I'm aware of, subscribe to the weak notion of authenticated data. Another interesting question is, which security level should high-level cryptography target? So my simple answer to you is that you should always target a 256-bit encryption with the 128-bit authentication tag. So why so large? Why do we need 256-bit keys? There are many answers to that question, and most of those answers are equally valid and plausible, but the one answer that I want you to remember from my talk, from my presentation, is that we need 256-bit keys in order to allow for potential biases in our cryptographic key generation. So what do I mean by bias? What is this thing bias? So let me graphically show you what I'm talking about. So if you have a good random bit generator that has no bias, and that random bit generator produces a sequence or stream of bits, every bit having a probability of being 1 or 0, that probability is split evenly in the middle. That probability is 50-50. So this should be relatively intuitive to most of you. This is what you would normally expect from a good random bit generator. So compare that to a biased random bit generator, where the probability is slightly skewed. So the probability of getting 1 is now 56% rather than 50, and the probability of getting 0 is now 44% rather than 50. So visually, if you look at it, it doesn't seem like it's that big of a deal, right? But it turns out that numerically, the bias is quite large. It's 25%. So that's what I mean when I say bias. So now that we are equipped with this understanding of bias, we want to calculate how much entropy are we actually going to get by getting a certain number of bits from our random bit generator. There is a formula for that. You can see it on the screen. And the important thing about the formula is that it has only 2 variables. It takes the bias, which is something that we've just covered, and it takes the number of bits that you produce from the, or you extract from that random bit generator. So let's plug in some numbers into that formula and see what we get. So we will use the 25% number for the bias. So we're going to assume that we are dealing with a very heavily biased random bit generator. So in practice, you should not be running on operating systems with such a biased random bit generator. But let's assume that we do. And we are going to ask our random bit generator to get us 128 bits because we're going to create a 128-bit key. And when you plug in the number, you end up with 53 bits of entropy. Not only is this a lot less than 128 bits that you would normally expect from a good random bit generator, it is also practically broken. It is, in other words, brute forceable with modern technology. Let's try to increase the bit space. So we'll use the same biased bit generator, the same 25% bias, but we'll do it over a 256-bit key. The formula scales linearly, So now we will end up with 106 bits of entropy. Yes, this is drastically lower than 256 bits that you would normally expect, but 106 bits is not that bad, because even with modern technology, it is practically unbreakable. It is high enough to be unbreakable with the technology that we have today. So just to summarize the first section, I do encourage everybody to use a very well-designed high-level crypto API library. Either find one that you like, or, I don't know, petition Microsoft to create one for you. You should also look at APIs where there is good streaming support. You want to use good streaming crypto APIs, because in many cases you're dealing with streams of data rather than fixed amounts of data. You should all be using 256-bit keys as your minimum length for the reasons that I covered. And do bear in mind that even though you will be doing high-level cryptography, it's not problem-free. High-level crypto, just like any other crypto, can still leak confidentiality, and in many cases, it's still something that we need to think about and worry about for your respective use cases. So let's switch gears, and let's delve into the second part of my talk, where I'll cover asymmetric and hybrid cryptography. So we'll start with RSA. How many of you are comfortable with RSA? How many of you know how to use it? Okay, so I see maybe half of the hands going up. So this was a somewhat of a trick question, because we'll test your comfort level, or I will test your comfort level. So the next set of slides is specifically for people who have used RSA in .NET before. But before we delve into it, let's do a very quick refresher on RSA, just so that we're all on the same page. I know some people may have forgotten or might be a bit rusty with RSA. So we'll start with our actor, in this case Alice, who uses a random number generator to generate two keys, a private key and a public key, both comprising a key pair. And there is another actor, we're going to call him Bob, who wants to encrypt a message to Alice. The message is hello Alice, and in order to do that encryption, Bob uses Alice's public key to generate ciphertext. Bob then somehow delivers that ciphertext to Alice, and in order to decrypt that ciphertext, Alice then uses her private key portion of the key to do the decryption and get the original plain text back, which is hello Alice. So hopefully I've reminded most of you what RSA encryption is all about. So let's see if we can use it. So we'll create our RSA instance, and then we will try to encrypt some plain text. And the first thing that .NET forces us to do is to select a padding mode. So that's the first decision that we're all faced with. And just to cut the suspense, there are 5 different options. So padding mode is an enumeration. There are 5 different values to pick from. Which one are we supposed to pick? They'll have those weird names, PKCS1, OAEP, SHA1, etc., etc. So it's not obvious which one we're supposed to use. If you try them all, you will get the following picture. The last 3 just throw. The last 3 give you an exception, padding not valid. And the first 2 do not throw. Okay, fine. So let's use maybe one of those that does not throw. So we'll use OAEP SHA1 in this case. And we proceed to encrypt on plain text. But the interesting question is, what RSA key size did we just use? So we will try to write out the RSA key size. Would anybody care to guess what kind of key we would get? No? It's going to be a 1 kilobit key. And as many of you might already know, 1 kilobit keys are way too small for RSA. They're practically broken. And it's unadvisable to use that particular default, which basically means that we're going to have to set the key size explicitly. So let's try to do exactly that. Let's try to set the key size. So we check the documentation, and Microsoft documentation has this specific property called key size. It says that key size gets or sets the size in bits of the key modulus used by the asymmetric algorithm. That sounds perfect. That's exactly what we need, so let's use it. So again, we will create our RSA instance, and we will set the key size to a 3 kilobit key, which is what we want, and then we happily proceed to encrypt our secrets, and everything is fine, right? But then we have this sort of suspicion at the back of our minds, and we decide to write out the key size that we just used, just in case, just to make sure that everything is correct. Would anybody care to guess what the key size is? It's still 1 kilobit. There is another way to check our sanity. We can try to get at the key size via another method. We can try to export the public key component of the RSA key, hence the false parameter there. and we get its modulus, which is an array, and then we get the length of that array and we multiply it by 8 to get its size in bits. It will give you the exact same value, and it's also 1 kilobit value. So somehow it's not using the key size that you thought it would be using. So still too early to put this thing into production. All right, we don't really have the time to figure out what the hell is going wrong with that set of APIs. So you're going to abandon that avenue of thought completely, and you're going to switch to a brand new RSA implementation that Microsoft provided to us in .NET 4.6 and up, called RSA CNG, where CNG stands for Cryptography Next Generation. I mean, how cool is that? Everybody wants to use next generation stuff. This must be the magic cure to all of our problems, right? So let's use it. We will create RSA CNG, and then again, we will set the key size to 3 kilobit, and then we write it out, and we get 1 kilobit again. And to add insult to injury, when we ask it for its type, we've asked the factory to give us an instance of RSA CNG, and the factory gave us an instance of RSA Crypto Service Provider. Thank you, Microsoft. This is my personal feeling when I see something like that. Why Microsoft? Why are you doing this to us? After a lot of pain and mental anguish and frustration, you realize that the factory is not the way to go. It's actually the constructor that you're supposed to invoke. So we're going to invoke the RSA CNG constructor directly, and then we're going to write out the key size, and now we get a 2 kilobit value, which is a much better default that Microsoft has changed with RSA CNG. So far, so good. Then we try to set the key size to the 3 kilobit that we wanted all along, and we write it out because we know that we cannot trust anything in .NET world anymore, and we get our 3072 value back. Hallelujah, achievement unlocked. But remember, all we've done so far is just trying to create RSA. We haven't actually done anything with it yet. There are still other things to worry about. So for example, the default key sizes. How default are they? Are they really default? Let's think about that. The RSA factory itself can be overridden, or the implementation of it can be overridden or set in machine config, which means that that implementation can be outside of your boundaries, or the boundaries of your code or your scope. It can be changed underneath you by somebody else, by a system administrator, for example, which also means that the default key size can be changed underneath you. It's not something that you can rely on, which essentially means that you can never afford to trust the defaults of RSA. You always must set the key size yourself, and for good measure, write it out. So those default key sizes that .NET makes available to us, how good are they? So let's take a look at them again. There are two implementations of RSA in .NET, the older one based on Crypto Service Provider and the newer one based on CNG. And you see the default key sizes there. And I was thinking about what can we possibly use to compare those default values with. And the best thing I came up with is Bitcoin network. I apologize for mentioning the dreaded Bitcoin name here, but this has nothing to do with the coin or cryptocurrency at all. I'm purely focused on the network, right? It's a large distributed network, and the interesting thing about it is that it has a publicized hash rate. And the current hash rate of that network is 2 to the power of 64 hashes per second. And it changes every month, it grows, which is roughly equivalent to 2 to the power of 90 hashes per year, and that was as of February, so by now I assume it's even larger. We're also going to assume that hash is an equivalent of a basic operation, even though it's not technically accurate because hash itself is a more complex, more convoluted operation with many basic operations in it. But just for simplicity, we're going to equate the two. We're going to assume that hash is an example of a simple operation. And if you read all kinds of cryptography books written by actual professional cryptographers, and not somebody like me, you will realize that 2 to the power of 70 basic operations are enough to break RSA with a 1 kilobit key. And in BCN terms, it will take roughly 1 BCN minute on that distributed network. And if you try 2 to the power of 90 basic operations, you can break an RSA key of 2 kilobits, which in BCN time is an equivalent of 1 BCN year. So the message here is that both of these are very troublesome, and it's easily achievable with modern technology of today that exists today all around us, which only underscores the fact that you do need to use an explicit RSA key size, and not just any key size, but a sufficiently strong key size. And I do recommend at least a 3 kilobit key, or if you can afford it from the performance perspective, go to the 4 kilobit key. In terms of the private and public keys, it's also not that trivial in .NET to figure out how to actually export the keys themselves, because the keys are something that you work with often. So here are the two instantiated RSA instances. I'm using a 4 kilobit here, but it doesn't really matter. the crypto service provider-based one called RSA1 and the CNG-based one called RSA2. This is how you would extract the public and private keys using the older one, and this is how you would do the exact same thing to extract the public and private keys of the newer one. The thing to note about this code is that the two APIs are very different, right? The code is different, the methods are different, the parameters are different. And the other thing to notice here is that if you look at the public keys alone, the size of the public keys in bytes is relatively comparable. They're roughly half of a kilobit. But when you look at the private keys, the situation is drastically different. The newer one has a much smaller key, private key than the older one. So just bear that in mind. Make sure you know and are aware that there are two different incompatible import and export APIs, and just be consistent. Stick to one of them and use it consistently. Don't mix them. So now it's time to actually do something with RSA. We haven't actually done anything with RSA. We only tried to instantiate it. So let's actually encrypt something using RSA encryption. We're going to create our plain text called data. We'll generate a byte array, and then we will use RSA.encrypt to encrypt it with one of the paddings that has worked for us, that didn't throw an exception. But in this case, the moment you try it, you will immediately get a cryptographic exception. The parameter is incorrect. Which parameter? I have no idea. And probably neither does Microsoft. So we're going to try every single possible conceivable padding type, and we will quickly realize that we get the exact same exception for all of them. So it can't be the padding. It must be the data, right? So what's wrong with the data? What did we do to the data? I don't know. Let's try to half it, and we'll just cut it in half. So we'll use our new smaller data, and we'll use the exact same encryption code, and now it seems to work. That's interesting. But then we remember that we've used SHA-1 padding, and many people have told us that SHA-1 anything is actually wrong and bad and unadvisable. SHA-1 has been known to be officially a cryptographically broken hash function, and our auditors and our compliance department is really pushing us to get rid of SHA-1 anything in our code bases, so we are ready and happy to oblige. So we'll do just that, so we'll just replace the padding. So we'll just switch from SHA-1 to SHA-256 just to make the auditors happy. So we try it with the new SHA-256-bit padding, and we get the dreaded cryptographic exception. The parameter is incorrect again. How lovely. So what ends up happening here is that apparently the data size limit that you can pass to RSA encryption is a function, it's a dependency of not only the padding, but also the key size. It's some function of the two. So that obviously begs the question, what is the magic formula? What is the magic formula for the maximum data size that you're allowed to pass to RSA encryption? Is there such a magic formula? The answer is yes, there is a formula that allows us to calculate it. You can use this method called getMax data size for encryption. You pass it the padding, it takes the key size from the RSA instance, and it gives you the maximum allowed data size. The biggest problem with this method is that it doesn't exist. I just made it up. And the reason why I made it up is because I'm trying to get my point across that the very basic information that you and we all as developers need in order to use RSA and use it correctly is not available to us. Thank you, Microsoft. So let me summarize the reasons to avoid RSA, even for signatures. As I've hopefully been able to show you .NET RSA APIs are really poor. RSA forces you to make all kinds of decisions on padding, in terms of padding, data length, et cetera, which is undesirable. If you want to target a 128-bit security level, you need to go to at least a 4-kilobit RSA key, which is quite large. It's hefty, fat, and chunky. So in terms of the actual numbers, if you look at the sizes of the private key, public key, and the signatures that it would produce, you're looking at a kilobyte, half a kilobyte, and half a kilobyte, respectively. So those are large values, which might not be convenient for your use cases. If you want to target a 256-bit security level, you need to use a whopping 15,360-bit key with RSA. And the biggest problem with such a huge key in RSA is that it's completely unusable. On my laptop, the key generation alone for a single key takes more than a minute. So that's unusable in my book. I don't know about you. To To top it all off, in addition to this slow key generation, RSA itself, and I'm talking about fundamentals, so RSA as an algorithm rather than a specific implementation, whether by Microsoft or not, is slow for signing. So why do we care about it? Why do we care about signing speed of RSA? So for example, when you think about TLS, if you use TLS with RSA certificates, signing is the activity that happens on the server. We sign on the server and we verify on the client. And we as the developers usually care about the server. It is the server that we are entrusted with. It is the throughput and bandwidth of the server that we care about. Clients are another story for another day. There are way more clients out there than there are servers. So that probably summarizes neatly my personal feelings about RSA, hopefully yours as well by now. So without further ado, if I'm encouraging everybody not to use RSA, and RSA is to be avoided, what do we replace RSA with? What is there other than RSA if we need to do the same things that we currently use RSA for? So I'd like to introduce you to modern elliptic curve-based crypto primitives that we can use to replace RSA with. So the first algorithm that you should all be aware of is something called digital signature algorithm, and all of them start with EC because all of them are over elliptic curves. So digital signature algorithm is an algorithm that will allow you to replace RSA signatures. So if you're using RSA today for signatures, you can use DSA for the exact same purpose. If you want a code sample, there is a link there. There is a very nice, easy-to-use code sample there. And by the way, it's natively supported by .NET framework. So this is not something that somebody has built from scratch. This is natively supported and ships with .NET framework. Another important algorithm is called IES, Integrated Encryption Scheme. It's an algorithm that can allow you to replace hybrid RSA encryption. If you're currently doing hybrid RSA encryption, wherein you are generating a symmetric key, you're encrypting your data with that key, and then that key is itself wrapped with RSA encryption. So you can use ECIES to replace that kind of scenario with. Again, there is a code sample link there if you want to play with it. And last but not least, another very important algorithm is Diffie-Hellman key exchange over elliptic curve. In Microsoft API nomenclature, it's commonly known as ECDH. You can look for APIs that start or contain the characters ECDH. It will allow you to create or negotiate rather symmetric encryption keys between the two parties with known public keys. And in certain other circumstances and usage modes, it will also allow you to achieve forward secrecy. Again, there is a code sample there if you want to play with it and test it out for yourself. So just to summarize the asymmetric part of the talk, obviously use high-level crypto APIs that do not require you to make decisions that you're uncomfortable making and shouldn't really be making. Try to abandon RSA. Now, I do realize that this is easier said than done. We are all working on large existing applications where completely replacing, refactoring, or removing RSA might not be possible or even achievable. At the very least, if you cannot get rid of RSA entirely, try to learn how to use it correctly. So make sure that when you do use it, you use it correctly. Try to get comfortable with modern elliptic curve-based cryptographic algorithms, such as ECDSA, ECDH, and IES. I don't have time in this talk to give it full justice that it deserves, unfortunately. I think it's a great topic for another talk by somebody else, so I do encourage the organizers, if they hear me, to put that or add that to the agenda. And last but not least, try to think about your goals. High-level cryptography is not a panacea. It doesn't cure or solve all of your problems, unfortunately. There's a quote that I like. Cryptography doesn't solve problems by itself. Symmetric encryption merely turns your data confidentiality problem into data management problem. I think it's a very true statement and something that I always try to keep in mind. So some recommended resources for you. There is a semi-decent high-level cryptography library called security-driven Inferno with decent documentation. So if you're looking or you're trying to just get a head start with high-level crypto, it's something that you might want to check out. There is a great book called Serious Cryptography by Jean-Philippe Omasson. It provides a great overview of the modern state of the art of cryptography. And if you're interested in something like that, I do encourage you to check it out. There is a book that I've authored called Application Security in .NET Succinctly. It's a free ebook, freely available. It provides even more coverage on the various .NET security pitfalls. If you're interested in learning more about that, then check that out as well. And last but not least, there is a great SlideShare presentation by Vladimir Kochetkov, which covers at a simplistic but good level the basics of application security theory, and it explains the different causes of insecurity and lack of safety and other important foundational topics and concepts. So it's a good read if you haven't seen it already. So before I get into questions, that's all I have prepared for you in terms of my main talk. I do have some bonus slides. How are we doing on time? So I think we have some time available. So let me run through my bonus slides, and then I'll open the floor to questions. So remember when I was talking about the 4 stages of Crypt Enlightenment, there was this last rare stage where it said that the beta solution might not need crypto at all. So what do I mean by that stage? Would you guys like to see an example of something like that? So let's quickly go through something that could be an example of it. Let me bring you to CSRF, or cross-site request forgery, which is a classic .NET protection mechanism that allows .NET to offer protection against a class of attacks such as cross-site request forgery. So in this particular model, we have a user agent, which is usually a browser with a user sitting behind it, trying to communicate with the server. The user would send a GET request to the server, and the server would respond with 2 things. It would respond with a CSRF token, which actually gets hidden and captured and encapsulated in an HTML hidden field. It actually gets encoded there. And the second thing is that that very same token is also attached to the response as a cookie, as a header. The user does some processing, hopefully fills a form, and then the user does a post. And that post goes back to the server with both of those tokens on the post. And the server checks that both of those tokens are received. That's the first thing that gets checked. And the server also checks that both of those tokens are matching. And that matching of the tokens is what allows the server to offer this defense against CSRF. So this is a classic mechanism that's built into ASP.NET and ASP.NET Core. And Mikhail Sherbakov did a great presentation that covered CSRF in its nitty-gritty details. So the problem or the issue with this classic approach that's part of ASP.NET is that this CSRF token generation and validation uses encryption. And the challenge with encryption is that encryption itself is a complex, expensive operation. It takes CPU, puts load on the CPU, it takes memory, it introduces latency. It's not really desirable. On top of that, this HTML token that the server injects, that injection itself is a very complicated, messy, and inconvenient process. And in many cases where you're doing AJAX, when you're doing asynchronous calls, it's something that is your burden as a developer. You now need to mess with those tokens, you need to extract them, you need to manually append them as headers. It's not a pleasant experience. For those who have worked with something like that, it's not a pleasant experience. So there is a way to approach this from a different perspective where the same or comparable CSRF defense can be mounted without any crypto at all. Now, I know this is a complicated, convoluted, busy slide. I'm not going to cover it right now, and you don't even, if you want to, you can obviously take pictures, but I'll be more than happy to cover it in all its detail and raw glory in the discussion zone if you're interested in something like that, if you're interested to learn how CSRF defense can be achieved faster, better, smoother, with no development influence at all. I do encourage you to follow me to the discussion zone, and I'll cover it, or any other questions. So with that being said, thank you very much for indulging me. You've been a great audience, so let me open the floor to questions. Thank you.
Hello. Можно на русском, да? В принципе, мы, когда шифруем какие-то текстовые сообщения, обычно используем симметричные механизмы шифрования, например, AES, а Rsa используем для подписи и для выработки какого-то там сессионного ключа. Вопрос, если мы переходим на механизм шифрования с использованием эллиптических кривых, можем ли мы начать шифровать им строки, или нам по-прежнему нужно поддерживать 2 механизма, симметричный и асимметричный? Спасибо.
Great question. So the question is whether or not, I guess, you can live just with the asymmetric cryptography, or you still have to follow the hybrid approach. You still need symmetric and asymmetric. And yes, you still need both. So you would still do your encryption the symmetric way. You would generate the key, and then you would do the symmetric encryption the way you're used to doing it right now. The question is, how do you go from there? How do you make sure that your key is intact, that your key is trusted? And that's where the asymmetric part of it comes in. So to answer your question, you still need both, right?
So first of all, thanks a lot for your speech. And the question is, what about timing attacks and high-level API? So does libraries like Inferno provide some mechanism to protect against time attacks, and does it provide some constant time functions? And as far as I know, for example, on architectures like ARM, you can't simply do time constant cryptography because of, for example, multiplication isn't time constant.
Right.
So does it
it's
handle
a
somehow?
Great question. So in terms of the timing functions or constant time functions, Inferno itself has constant time comparison functions if you just need to use the function itself for something else unrelated to what Inferno itself provides. In terms of the actual encryption, Inferno itself does not reinvent any other crypto primitive. No crypto primitives have been built within Inferno. Inferno just piggybacks on top of what's provided by Microsoft. And the specific crypto primitives that Inferno is using are built around the AES-NI instructions provided by Intel. This is all done by Microsoft. This has nothing to do with my library or that particular library. It's something that's part of the Microsoft Windows API. And the AES-NI instructions themselves are time safe or time attack safe. It's been validated by Intel. There is a NIST certificate around that. So as much as you trust NIST, it has already been validated, vetted, and proven that timing attacks will not occur within the AES code itself.
Еще вопросы, пожалуйста.
Все, вопросов нет. Спасибо большое, Сэн.
Thank you.